Let us now consider another topic, the directional couplers. So, a directional coupler is a 4-port device. So, we can see that a directional coupler has an input port, a through port, a coupled port and an isolated port. Power incident in port 1 is coupled to port 2 and port 3. In an ideal directional coupler, the incident power is not coupled to port 4, and therefore, this port is called isolated port. Power gets divided between port 2 and port 3. Now, the parameters which are defined for a directional coupler are coupling, directivity, isolation and insertion loss, and usually they are expressed in dBs or decibels, and we can write coupling C is equal to 10 log, this is log base 10 P1 by P3. That means, we take the ratio of the input power and coupled power in port 3, and when it is expressed in dB, we get C is equal to 10 log P1 by P3. Similarly, directivity, it gives the ratio of the power between port 3 and 4. Isolation is between port 1 and 4, and I is 10 log P1 by P4. The insertion loss or L, it is 10 log P1 by P2. So, this is one symbol which is used to represent directional coupler. Another symbol which is also commonly used in representing directional coupler is shown here. The scattering parameter of a reciprocal 4-port network matched at all ports, it is given by S equal to, the diagonal elements are 0 because this 4-port network is matched at all 4 ports, and since it is reciprocal, so we have S21 equal to S12, S31 equal to S13 and so on. Now, when the directional coupler is ideal and it is lossless, we have port 1 and port 4 and port 2 and port 3, they are completely isolated, and therefore, S23 S14 is equal to 0. Now, what we can do by proper choice of phase references, let us set S12 and S34 to be a real quantity alpha, alpha is less than 1. So, this S12 and S34 set equal to alpha, and S13 equal to beta e to the power j theta, and S24 is magnitude is same as S13, but it has a different phase. So, S24 is beta e to the power j phi, and alpha and beta are real quantities, both less than 1, and theta and phi, these are phases associated with these S parameters and defined with respect to the terminal planes. Now, if you take dot product of rho 2 and rho 3, then what we get? S12 conjugate S13 plus S24 conjugate S34 is equal to 0. We get the same from columns 2 and 3 as well. And if we now substitute these values, so S12 conjugate will be alpha, S13 will be beta e to the power j theta. So, this term will be alpha beta e to the power j theta. S24 will be beta e to the power minus j phi, and S34 is alpha. So, it is alpha beta e to the power minus j phi, and therefore, we now get e to the power j theta will be equal to minus e to the power minus j phi. So, this minus can be written as e to the power j pi, and therefore, we will get theta equal to pi minus phi, and therefore, theta plus phi will be equal to pi, and in fact, this relationship will be true for theta plus phi is equal to pi plus minus 2 n pi, and what we do? We ignore this factor plus minus 2 n pi, we only consider theta plus phi is equal to pi. Now, we consider two cases. Case 1, when theta equal to phi is equal to pi by 2. In that case, the phase constants are equal and the coupler will be a symmetric coupler, and for which the S parameters will be given by 0 alpha j beta 0, alpha 0 0 j beta 0 0 alpha, and 0 j beta alpha 0. Another case, when theta is equal to 0 and phi is equal to pi, this case it is an asymmetric coupler, and we can see that these two betas S13 and S31 they are equal to beta, but S24 and S42 they are minus beta, and alpha and beta these are dependent on each other, and it is given by alpha square plus beta square is equal to 1. We take any column, then if you multiply with the complex conjugate of the corresponding elements and add them, then we get alpha square plus beta square equal to 1. In both the cases, this relationship is valid. So, we have magnitude of S13 square is equal to beta square, and then S12 square is alpha square, and that will be equal to 1 minus beta square. And we can write the parameters of the directional coupler in dB as, now C becomes the coupling 10 log P1 by P3, and P3 by P1 is mod S13 square, which is beta square. So, once we substitute here 1 by beta square, we get C is equal to minus 20 log beta. Similarly, D, the directivity, it is 10 log P3 by P4, and this can be, this P3 by P4 can be written as P3 by P1 and P1 by P4. So, P3 by P4, P3 by P1 can be written as 1 by beta square, and similarly P1 by P4 can be written as 1 by mod of S14 square, and therefore, D can be written as minus 20 log beta by mod of S14. Isolation I, we can write directly 10 log P1 by P4, and this will become minus 20 log mod S14, and insertion loss 10 log P1 by P2, this is minus 20 log mod S12, and from here we find that S12 modulus is essentially alpha or under root 1 minus beta square. We further note that if we add C and D, then we get 10 log P1 by P3 into P3 by P4. So, P3 terms will get cancelled and we will be left with 10 log P1 by P4, which is I, and therefore, I is equal to D plus C in dB. So, we have defined different parameters of a directional coupler. Let us turn our attention to waveguide couplers. Waveguide couplers appear in various form. Common ones are Bethe-Hole coupler, multi-hole coupler. The coupling can be made between two waveguide sections. Either the coupling between two waveguide sections joined either on the broad wall or at the narrow wall can be made by drilling suitable aperture on these common walls. For illustration purposes, we will consider here a two-hole coupler. So, in a two-hole coupler, as we can see, we have two waveguides, they are stacked one over the other, and therefore, we have a common broad wall for both the waveguide, and we have holes made on this common wall. So, it consists of two rectangular waveguides coupled by two identical apertures on the common broad wall. The identical apertures are separated by a distance which is a quarter of the guide wavelength, that is lambda g by 4. Fields with different amplitudes are radiated by the aperture in forward and reverse direction. So, when the signal will incident on this waveguide, a part of the power will get coupled to the other waveguide, and this coupled power will travel both in forward as well as in the backward direction. Now, this coupling or the amount of field that is coupled in the forward and backward direction, these are different. Now, let us consider a wave with unit amplitude which is incident at port 1. So, this is the port 1, and let BB and BF be the coupled field into the second waveguide. Now, BF is in the forward direction and BB is in the reverse direction. Now, this BB and BF, these are known as aperture coupling coefficients. So, we assume that this first aperture, it couples only a very small fraction of the incident power. So, what happens essentially, the amplitude of the incident wave at this second aperture, when the wave reaches at the second aperture, it remains essentially unity. Now, the wave which actually travels over this distance d, now we can see that if BF representing the coupling from the first aperture, in the second aperture, because of this distance d, the amount of field that will be coupled is BF into e to the power minus j beta d. Because the wave was 1 here, here it becomes e to the power minus j beta d. Now, this forward wave BF also travels this distance d and appear in phase with the waves that is coupled from the second slot. So, what we observe is that after in this plane BB, we have the waves, coupled waves from the first slot and the second slot, they appear in phase and they are given by BF e to the power minus j beta d. Whereas, regarding the reverse wave, we find that here it was BB, now here from the second slot, it will be B b e to the power minus j beta d, and then this wave will travel again another length d. So, we will have this second wave having a phase shift of 2 beta d, and therefore, the total forward wave at plane B b is B f e to the power minus j beta d from the second slot, again B f e to the power minus j beta d from the first slot, and therefore, it is 2 B f e to the power minus j beta d. And at the plane A A, the total backward wave will be given by B b plus B b e to the power minus j 2 beta d, because we get this backward travelling wave which is given by B b e to the power minus j beta d is will suffer another phase shift because of this length d. So, we find the forward waves will always add in phase and the backward waves will always add out of phase whenever 2 beta d equal to n pi and n is equal to 1, 2, 4. So, if we have here B b plus B b e to the power minus j 2 beta d, and suppose we have 2 beta d is equal to pi for n equal to 1, then we have 2 pi by lambda d is equal to pi, and therefore, d by lambda is equal to 1/4. So, if we take this d to be equal to lambda by 4 or rather lambda g by 4, where lambda g is the guide wavelength, then the backward waves can be cancelled at this plane A A, and we will be left with only the coupled signal at this plane B b. In general, we define coupling C to be equal to minus 20 log 2 magnitude of B f, and directivity D, it is given by 20 log 2 mod B f divided by mod B b mod of 1 plus e to the power minus 2 j beta d, and this can be written as this term 1 plus e to the power minus 2 j beta d can be written as cos beta d. Therefore, d becomes 20 log mod B f divided by mod B b mod of cos beta d. And this can be expanded as 20 log mod B f by mod B b plus 20 log mod of sec beta d. We should note that the coupling C here is not frequency sensitive, as B b and B f are slowly varying functions of frequency. However, if we look at the directivity term, the directivity D is frequency sensitive because it has this factor sec beta D. So, we can see that if we want to design a two hole coupler, we need to know these two parameters, the coupling coefficients BF and BB, and once we have these values, we can design a directional coupler of the specified coupling and directivity. Now, the values of these coupling coefficients depend upon the radius of these apertures, and these coupling coefficients for this type of waveguide geometries can be estimated analytically. However, we will not consider this here. We assume that these coupling coefficients are available with us while designing this type of two hole directional coupler. This concept what we have discussed can be extended to multi-hole couplers, because if you notice here, the parameter D is very frequency sensitive, and therefore, this type of two hole coupler will have relatively narrow bandwidth, and if we go for broadband, if we want broadband operation, we can go for design of multi-hole couplers, and where we can actually design coupler for a specified bandwidth by controlling the coupling coefficients at different aperture locations. Directional couplers have lot of applications. We discuss here one example of such application. So, we are employing this directional coupler for monitoring the power that is supplied to this antenna element, which is the load, by this transmitter. Normally, this transmitter will send large amount of power to the load, and by employing this directional coupler here, we sample a small fraction of the power in this port 3, where we perform the measurement by connecting a power meter, and we put a matched load in the port 4. For example, if we have C is equal to 30 dB, then P1 by P3 is 1000. That means P 3 is 1000 of P 1, which is actually 0.1%. So, this measurement port will get 0.1% of the power, whereas the load will get 99.9% of the total power. We are assuming port 4 is isolated, perfectly isolated, and does not get any power from the transmitter. So, by monitoring the level of power here in this port, we can know how much power is being delivered to the load. So, we are essentially measuring a very small fraction of power to know a large amount of power that is being delivered to the load. It should be noted that because of some load mismatch, if any power is reflected from the load, then it will appear at port 2. Now, port 2 and 3, they are isolated. Therefore, this reflected power will not appear in the measurement port and will affect the measurement. This reflected power will get divided between port 1 and 4, and in port 1 it may be absorbed by the impedance of the transmitter, and whatever power goes into the port 4, it gets dissipated in the mesh load connected here. So, this is how we can use a directional coupler in monitoring of power. So, we have discussed different aspects of directional couplers. In the next lecture, we will consider another useful microwave device, a microwave filter.